Hey guys, and welcome back. Today we're going to be talking about checking the solutions of a linear system. We're going to figure out if certain points are actually solutions to systems. And as our learning target, it's still going to be to solve a system in two equations and two variables. We're not actually going to solve the system today. We're going to be taking solutions and making sure that they are, in fact, the actual solutions to the system. So our success criteria today is going to be to identify the solution to a system of equations given the graphs. Okay, so just being able to tell me if something is a system, and we're going to be able to justify whether that solution is actually with that certain system. Justifying means showing the work that backs up why you think that is a solution to the system. So let's take a look at our key idea here. I have a little recall sentence here, meaning this is something that you have already been told. A solution to a system is an ordered pair or a coordinate with x and y where the two lines intersect. So if you look at my diagram below, I have an intersection point of this system at 1, 1. That means that x equals 1, y equals 1, and whatever system that these two lines create, the x being 1 and y being 1 is the solution. It actually fits into both equations. So let's take a look at the first example. It says create a system for the following situation and graph. Charisse is a florist and wants to make an arrangement of tulips and daisies for a client. The client has specified she would like a dozen flowers in her arrangement. Charisse informs her that the tulips cost $3 per flower and the daisies cost $2 per flower. And the client tells her she wants to spend a total of $30 on the entire arrangement. The first part of this example that is giving us any type of numerical values is the sentence, the client has specified she would like a dozen flowers. It doesn't say which flowers she wants, though, how many of each flowers she wants in her arrangement. All we know is that there are tulips and there are daisies. So let's first identify our variables. Let's call x the tulips, and let's call y the daisies. So when we create our equations, first let's just deal with the amount of flowers. So we know that no matter how many tulips or daisies, they have to add to equal 12. That's what a dozen is. So I have so many tulips plus so many daisies is equal to 12. So that had to deal with amount of flowers. We want to group units together. So you don't want to mix money and amounts or vice versa. Now, the next equation we're going to create is going to have to do with money. So the sentences that hold the numbers we want here, change my pen. There we go. I see tulips cost $3 per flower, daisies cost $2 per flower, and they want the total bill to be $30. So let's create an equation that shows us the total costs. Well, in order to get the cost for the tulips, we have to take $3 and multiply it by the number of tulips. And then we also have to add the $2 times the number of daisies. And then we want that to equal $30. And that had to do with the money. That equation had to do with all of the money. Now we need to be able to graph these two equations. And if you notice, they're not in y equals mx plus b. Y equals mx plus b is how we usually graph things. So we're going to need to rearrange this into y equals mx plus b form. So just remember, y is alone in y equals mx plus b. So as long as you solve for y and put everything else on the other side of the equation, you will get y equals mx plus b. So in the first equation, y is right here, and that means we need to get rid of the x. The x is positive, so we need to subtract it from both sides of the equation to get it to travel to the other side. So x plus y minus x is equal to 12 minus x. So x minus x, that's 0. and we're left with y is equal to, now you can switch these two around. So instead of writing 12 minus x, you can write negative x plus 12, because the 12 here is positive. The x here is negative. So as long as you switch them around and carry the sign with them, you still create an equation that is true. And this is in y equals mx plus b. We can do the same thing in the second equation. I want to isolate this y, which means first you have to work furthest away from the variable first. We got to get rid of this term first, not the 2. So again, it's positive, so I'm going to subtract it from both sides. 3x plus 2y minus 3x is equal to 30 minus 3x. The negative 3x and the 3x become 0. And I'm left with 2y is equal to, again, I'm going to switch this line around. That's going to be negative 3x plus 30. And then now we can get rid of that 2. So we divide by 2. But remember, we need to divide everything by 2. So we need to divide this term by 2, and we need to divide that term by 2 on the other side of the equal sign. So this one turns into y equals negative 3 halves x plus 15. Now we're ready to graph because we have both equations in y equals mx plus b form. So my first equation that I need to graph, I have a y-intercept of 12. So I'm going to plot that first. 12 is right there. And then we need to fall 1, run 1, because if it's just negative x, that means there's a negative 1 there. So we're going to fall 1 and run 1 to the next point. Fall, run, 1, 1. Fall, run, 1, 1. And you don't have to make 4 points. All you really do is need to make 2 points, but I made a couple just because they were pretty close together and I wanted to make sure my line was straight. Okay, now we can apply it to the other equation, which, let's see, I wrote negative 3 halves x plus 15. So we need to plot that 15 on the y-axis first. Then we can fall 3 and run 2. I'm going to make this a red. Okay, so here's my y-intercept at 15. Then we need to fall 3, run 2. I'm going to do that a couple more times. Fall 3, run 2. Fall 3, run 2. Fall 3, run 2. I did it a few times just because I wanted to make sure I saw exactly where the two lines, whoop, didn't mean to flip my screen on you guys, sorry about that. I wanted to see where the two lines intersect. So that's my system of equations. So not only did I create the system, but I manipulated the equations so that it was easy for me to graph in y equals mx plus b. Now I'd like you guys to give this a try. You're given your own system. I want you to create it. First, define your variables. Ask for help if you need it. This is a tough example, so make sure you raise your hand and ask for help if you need it. So identify your variables and start to construct two different equations. One having to do with the total bags of popcorn and the other having to do with the price. Alright, so we're going to solve this exact same problem. We're going to create a system and graph it, but we're going to graph in an alternative way. The equation that we came up with in example 1, we're just going to copy down the system that we already made. We said it was x, whoop, I don't know why it's not giving me a pen. There we go. X plus y was equal to 12. And then we also had the equation 3x plus 2y equaling 30. Now, in the previous example, we rearranged it so that these equations were in y equals mx plus b. This method, and I'm actually going to write this method's name next to the word alternate. Ooh, don't want to move my screen. Okay, next to the word alternate, this is going to be the intercept method. Okay, we should know that a y-intercept is where it crosses the y-axis. Well, there's also an x-intercept as well. The rule here is plug 0 in for opposite variable. So if you want the y-intercept, plug 0 in for x. If you want the x-intercept, plug 0 in for y. So if I were to take the first equation and plug 0 in for x, 0 plus y equals 12. Well, that means that y must equal 12 because 0 plus 12 equals 12. So the y-intercept is equal to 12 in the first equation. If I were to plug 0 in for x, or excuse me, in for y, I get the same result. X plus 0 equals 12. So 12 plus 0 equals 12. That means the x-intercept must also equal 12. The intercepts are not always going to match each other like that. For instance, in the second equation, if we were to plug 0 in for x, we get 3 times 0 plus 2y is equal to 30. Well, 3 times 0 is 0, so we just have 2y is equal to 30. Well, 2 times what is equal to 30? 15. So the y-intercept here is equal to 15. Now I can do the same thing and plug 0 in for y. So 3x plus 2 times 0 equals 30. Well, 2 times 0 is just 0, so we have 3x is equal to 30. And if we divide by 3 on both sides, or we think about what times 3 equals 30, we get 10. So the x-intercept is equal to 10. So now that we've done this quick calculation, we can go ahead and start graphing without even rearranging the equations at all. Remember, intercept just means where they cross the axis. So for the first equation, we said the y-intercept was 12 and the x-intercept was 12. So I just need to locate 12 on both axes and connect the dots. I'm going to make this line blue. So here's 12 on the y-axis. Here's 12 on the x-axis. Connect the dots. There's your line. And it's going to be the same line that we made in the first example. It's just using 2 different points. And actually, one of the points is the same. It's still the y-intercept. Okay, and then the second line, I'm going to color that in red. We had a y-intercept of 15 and an x-intercept of 10. So I'm going to mark 15 on the y-axis. It's right there. And I'm going to mark 10 on the x-axis. So now I can clearly see where the 2 lines intersect. And if I were to compare, I'm just going to show you guys here. If I go back a couple of slides, it looks exactly the same as the first drawing I made. It's just a different method of going about it. So instead of changing the equations into y equals mx plus b, you can use this intercept method instead. Why don't you guys give this intercept method a try in your U-Try? right, so this example is actually pretty easy, and you're going to see this a lot on your test. It says, is 2, 4 a solution of each system of equations, and explain your reasoning. So this is what we're going to do to check our answer. So let's say we actually solve the system and we think that 2, 4 is our answer. Well, we need to substitute it in to the system and make sure both equations are true. So we have A's system and we have B's system. We're going to see which system this point is actually a solution to. So how we're going to do that is we're going to take the 2 and plug it in for x and the 4 and plug it in for y. So in this first equation, I see 4 equals 2 times 2. Well, is that a true statement? Yes, 4 does equal 2 times 2. Let's do it on the second equation here. So I've got 4 is equal to 6 times 2 minus 8. Let's simplify the right side so that we can see if it's actually true. 4 is equal to 6 times 2 is 12. 12 minus 8 is actually 4. So it is a solution to the first system. Let's check and see if it's a solution to the second system. So we have x minus y, so that's 2 minus 4. Does that equal -1? Well, 2 minus 4 is equal to -2. So because -2 does not equal -1, I can already tell this is not a solution because it did not work for the first equation. Now we can plug it in for the second equation, but we really don't have to because we already know it doesn't work for one. And in a system, the point has to work for both equations or it's not a solution. So what I would like you guys to do is try this on your U-Try. Just plug in 3, -4 in for x and y in both equations and see if both equations are true. If it is a solution. All right, so I've got one last example for you. We are given a system and its graph already. We don't have to graph it. We're going to read where the two lines intersect, and then we're going to check and verify if that is in fact the solution to this system. So if we look at where the two lines intersect, I'm going to highlight that point right there. I'm actually going to name it as well. That coordinate is 2, -1. So now that I've read the coordinate, I'm going to do what I did in the last example and plug it in. I'm going to substitute x in for x and y in for y in both equations and see if it holds true. So I've got -1/2. Sorry, I forgot my y. So y, which is -1 in my coordinate, equals -1/2 times x, which is 2. Well, if you were to type -1/2 times 2 in your calculator, you get -1. So I get -1 is equal to -1. That's true. Now I need to check it in the second equation. Okay, well, y was -1, so -1 is equal to 3/2 times x, which is 2, minus 4. If you were to type 3/2 times 2, you're going to get 3. So I've got -1 equals 3 minus 4. Well, 3 minus 4 is -1, so that's also true. So since the coordinate 2, -1 worked in both equations, that means that that is definitely the solution. So I would like you guys to give this a try. Read the point off the graph and verify by plugging into the system.